Damn. That sucks. Well, sorry about that for the people who didn't make lecture today. I didn't, well, you can ask the people who are here to fill you in. So I'm going over acid. I mean, you can look at the slides. All right. So, but now we're resuming at least here. Okay. So now let's get, so that's isolation. So now there's another notion of isolation where it's kind of a perfect isolation. So that's like under, when you run things under serializable, under that isolation level. That means that basically you really do feel as if it's your own version of the database. And you know, anytime you do, you know, you work in the beginning of the database, you do a read there, and then you work more and more, and then you do a read again, and it's like there's nothing has changed. You don't. It really does feel like it's your own database, which is great until the database concurrency controller at one point reaches out and knocks you down and rolls you back. Because sometimes the database is reaching a weird state with other users that also have this perfect isolation of serializable. And the database system basically says, we cannot satisfy everybody. Someone has to die, and it might be you. So under, there's some different use cases. We'll get into the practicality of transactions and what that really means. But it means that basically, if you're doing under this kind of this perfect isolation where you're completely isolated, there is a chance that you will be without your, you know, you'll be aborted. The controller will decide that you have to go. And then the idea is then you restart, and then you go back to where you were. Okay, now durability. So I hope that's clear. Again, any questions, put them in the chat. Durability is a very, very critical property of a transaction. And let's face it, we don't get durability in the world today. So I don't know how many times you guys have called in to some business and said, okay, well, my new address is this, or you've gone into their system, you've changed your address, you've changed some data, right? Your email or something or other. And have you ever had the experience where it doesn't take? So in other words, like the next day, it's back to what it was. All right, probably because something overrode it, some automatic process, they were doing some kind of reconciliation. This is very common. I had this happen to me, especially, well, I don't really want to say, but I've seen it. I mean, there are certain systems when you're working with kind of, when you have to, when you're forced to interact with, I'll just basically say crappy systems and crappy, like companies that do a crappy job of this, what you'll get is you don't get durability on simple things like your address, or it doesn't, and that basically, we can ask where that comes from, but that actually is a transaction problem. So, but more in the classic sense, durability basically has to do with the fact that I do my transaction, I say commit, the system says you're committed, it better stick in the database. In other words, I don't want something that the controller to later on, like 10 minutes later, go, well, actually, we have to reverse you out of that transaction. Because I never get told that. So when it says commit and the date is in, I want to know that the date is in, no matter what. And even if right after they say commit, someone yanks the power cord out of the computer that I'm talking to, I still want to be guaranteed that it's in the persistent storage in the database on that computer. All right. So the way they get settled, just as a side effect, as a side comment, is that it gets settled with what's called write-ahead logging. So before you actually write to the database, you write a log out and verify that log got written to the file system, well, the database file system, and then you actually make the change to the data. Because at any moment or any point during that process, you have to assume that somebody can cut the power, right? So if you do that write-ahead logging, then if the power gets cut right as they're writing out the actual data to the database, what they do when they restore the database, they just do a redo operation on that write-ahead log, and then it's reflected in the database. Okay, so that just shows you the levels to which people go to guarantee durability. So durability is extremely important. Okay, I hope that makes sense, all that. So this should be very kind of intuitive understanding what this acid means. All right, so this right here, let's not really go into like too much of this right here. Let's just kind of like go down here and look at this example here. Can you guys see my pointer, by the way? I'm hoping. Can you see this pointer kind of wiggling around over RBAL?
Yes.
Good, thank you. So okay, so we have one transaction, all right? So this is kind of a banking transaction where it's going to compound 10%. It's going to give me 10% compound. This is it. I mean, basically in today's world, it'd be 0.001%. But anyways, okay, it's going to compound the balance in account number 15 by 10%. Okay, So basically it reads the number there, and then it compounds it, adds 10%, and then it writes it back out, writes out back what the value is for the account number 15. Okay, so that's compounding. The other one here is the withdraw. So it means that I'm going to basically, I'm also asking on that same day to withdraw 2,000 crowns from account number 15. All right, so it reads the balance, withdraws, and then writes out the new balance with 20,000 less or 2,000 less crowns. All right. So these are two transactions. These are two transactions that can be run through at the bank. Right. Now, the bank, of course, what's the bank going to want to do? Okay. The bank really does have the choice to run. Both make sense. You can't complain if you're a customer. You can't complain if they run T1 before T2 or T2 before T1. But no matter what, it has to be they run one transaction and they run the next transaction. That has to happen. We can't have this weird interleaving, which I'll show in the next slide, which would result in basically lost money and inconsistency and big trouble. Okay, so here we go. So here are two possible schedules. The one is that basically you have the initial balance here. The first thing it's going to do is compound it, turn it to 11,000 crowns, and then it's going to take away the 2,000 crowns, right? So then we're down to 9,000. Now, this is another way we're going to do it. We're going to do the withdrawal first, and then we're going to do the compounding. And just as an aside, which do you think the people down at the friendly bank are going to run if they had the choice? I mean, would they actually into their systems write in something that would kind of paste the transactions, you think? Yeah, I think the second one. They do this actually. They do this in trading too. It's called front running. I think that there's a lot of regulation around it, but yeah, it's their system. You can't complain if they run number 2. You can't say, oh, no, you can't, unless it's down to it like on a like the time second. You can't complain. So they're going to probably run the second one. But what they can't do are any of these, because what these do is these are intertwining in a very strange way, where what we have is we read about what's happening here is we're having what's called a lost update. So one of the anomalies you get if you just let all these transactions at the database willy-nilly and don't do any controlling at all, one of the main problems you'll get is what's called the lost update. So what that means, it means that one of them is going to write out the value, and the other one, they're both going to read the initial inputs to kind of make their calculation. One of them is going to write out the value, and the second one's going to come along and clobber that value with their own value. So the one transaction was completely lost, right? It was completely lost in the process. So that is what happened here. So basically what happens is this one's going to knock out transaction 2, and this one's going to knock out transaction 1, okay? So these are not to be permitted, okay? So we don't want to have this kind of thing happening. We want to control things so we get first one goes, and then the second one, or the second one, and then the first one, right? So I hope that makes sense. I hope that makes sense to people, why that would be desirable. Okay, so this right here is some formalism that I don't want to go into so much. I think you'll see it when we look at the actual examples. But the thing is, it's hard to really understand transactions completely, unless you guys have already had this. I mean, maybe some of you guys have already seen this stuff. It's fairly basic in computer science. But the thing is that this does require some study. I mean, transactions aren't that simple. You've got to kind of go back and study. So if you really want to kind of nail it down as a formalism, you can do it this way. Now, what's important here, and this is the right, so this guy, Jim Gray, who was one of the main innovators of ACID and transactions in general, he got the highest award in computer science, the Turing Award, for many things, but in particular for the following insight. And that is, the insight is that these are like read balance, compound balance. There could be an unending amount of this kind of pseudocode operations, right? We could be kind of like going and trying to, but you don't really, it's too specific to one particular application. What Gray was able to kind of do was just kind of lift all of that out and abstract the whole thing to something that's extremely useful and extremely basic. And that is to model everything as reads and writes. So basically what we have here now is we have like transaction 1 reads X, right? That could be the account, well, this is not, here, let me just show, here's the one, maybe the better one. Okay, if you guys see that. Okay, so in this case here, account number 1, this is like the balance for account 15. The first transaction reads it, then the second transaction reads it, and then the first transaction writes it, and the second transaction writes it. So this is an abstraction. This is an abstraction of let's see, write 2. So the last one. This is an abstraction right here of this schedule here, I believe. Although actually I would have to basically say, if I want to make this an abstraction, here, see the schedule here that we have right here? How do we model this using kind of like this lifting to kind of more of an abstract? We model it the following way. That is that 2 does a read, okay? Then it does its internal operation, which we don't have to model. That's the key thing. We don't have to model the internal operation of what it means to subtract 2,000 from an account balance. And then I believe now what happens is that then 1 reads, and then 1 writes, and then 2 writes. Okay, so these are the steps. This is a schedule. This is a schedule that corresponds to this more kind of specific set of operations in our example. Okay, and so what's happened here is that what we've done is we're modeling things with just excuse me, just reads and writes over a data object. So the data object here is account balance for 15, right? And as we'll see later when we get into the practicality of this, the granularity of these values, what they are is they're tuples. They're records in a table, right? So when you see X, and later on we're going to see Y. That's not right. I'm going to make that a lowercase x. All right. When we see like Y or something, just think of X, Y's, and Z's. Think of all those as just basic single records in a table, right? Because that's the granularity at which concurrency control works. Is at the tuple level for basically. There's a lot with concurrency control. I mean, one can always say there's more complexity. I'm trying to simplify things just to kind of keep everything really crystal clear. Okay, so this right here, this is a schedule of operations, and there's the definition on this slide here, which will kind of give you like the steps of the transaction. And here's a schedule. So basically, what a schedule is, if you take a set of transactions, a schedule is an interleaving of their operations through time. And interleaving isn't just arbitrary; it's interleaving where if an operation, let's say transaction 1, an earlier operation transaction 1 will always appear before a later operation in transaction 1. So when it does the interleaving, it respects the order the transactions are executing. That's all it is. There's some formalism around it here that's shown, but it's not really there's not really much more to it than that. Okay, so if we look right here, we're talking about serial schedules. So a serial schedule. So let's say, for instance, let's just take the ultra paranoid way of solving this problem. So right now we have a problem. We have the problem that if we allow for them just to kind of access willy-nilly 1 and 2, we get in a situation like this where this right here, 1's right on X gets overwritten by 2. All right, that's the lost update. So this is a schedule here that has a lost update. All right, and update of X, right? So it's being overwritten. Transaction 2 is overwriting transaction 1. Okay, so what's a real easy way to deal with that? Easy conceptually. Easy way of dealing with that is I say, for everybody who wants to come to my database, like for instance, if all you students wanted to kind of do an operation, like I had this database, and I want all of you students here to do an operation on the database. And let's say that it's post-COVID time where we're sitting in the same classroom. I'll basically say this. I want to enforce concurrency control. Here's what I'm going to do. I'm going to say, all of you guys want to do in reads and writes over this little database here. Everybody form a line. Take the first person, you sit down at the computer and do your work, right? Okay, good. Now you're done, move along, second person, all right? And we go through the whole set of people. What we're going to get out of that is we're going to get a schedule that looks like this right here, where the colors correspond to different transactions. So what we're going to get here is we're going to get a this is all the yellow transaction here doing all its work. That's transaction 1, then transaction 2, then transaction 3. Okay, so that right there is what's called a serial schedule, because all it is just a schedule that's just basically one of the ordering permutations on the transactions and just having them all do their work and then move on to so the next transaction can do the work. All right, but that's not practical. I mean, you can't run a database on the internet like that. I mean, you have to allow for concurrency, right? So we want to have it so people kind of all access the database and they feel like they're doing it simultaneously. Okay. We have a different notion of a schedule, more of a realistic schedule, where we do take in people's requests, right? But it's not exactly willy-nilly. We have some kind of control over the process. And we have control over the process so that what we guarantee is we guarantee a schedule that is not serial, okay, but is serializable. So in other words, it's equivalent to some serial schedule, right? It's exactly equivalent to some serial schedule. Now, as we're doing this, if we determine, oh no, someone's doing something where we can't guarantee that property anymore, then we're just going to have to kill somebody. We're going to have to kill one of the transactions. That's all. And then that'll free things up, and then we can kind of continue on that transaction that was killed. Maybe even give that transaction was killed a first in line thing for as the new transaction start. Okay, but that's what the real practicality of concurrency control is to maintain that kind of in real time as these operations come in, because you can never anticipate what the operations are a priori. You don't know beforehand what's going to happen. But the theory has to do with just kind of where we do kind of, we're not thinking the practicalities, but we're still kind of dealing with the theory. So let's try to get through that quickly. All right, so serializability has to do with, can we move something in? Can we move a schedule that was, not serial? Is it equivalent to some serial schedule? And there's two notions here. There's the truth, the ultimate truth of what is serializable or not. And then there is kind of what can we implement that is almost the truth, and it's actually kind of good enough. What can we implement that basically does this in real time and kind of ensures that the schedules that are actually being accepted are serializable. All right. Okay, so view serializable is our kind of truth definition. And the truth definition basically comes down to this. There's a lot of formalism here, and you can kind of look at it later. But basically, it's like this. We have a whole bunch of data objects, but in this case, let's just say we have X, all right? Well, X or Y, and Z. Okay, so we have 3 of them or whatever. Now, there's basically, what we do is we look at the conditions. There are these kind of conditions that are going on in the schedule. And the conditions are something like this, is that when something is read, when a transaction reads something, it's either doing an initial read, right? So it's reading it from the before days of the whole schedule, or it's reading from another transaction's write. Okay. So when you do a read, you're, either reading the initial or you're doing a read from another transaction's write. Okay. So basically you read from, so here's the formal definition of the read from. There's the initial read. And then finally, there's the notion of the final writes. The final, when you look at the very end of it, if you had a transaction at the very end, if it's kind of hypothetical transaction, well, who are doing the final writes? Let's just think of it that way. So all the final writes of the object. All right. Which transaction is doing the final write? Okay. So that's kind of so you have the initial reads. So I'm in a transaction. I'm transaction number 4471, and I'm doing an initial read of X, and I'm reading the Y from transaction 1142. Okay. Now those are my reads of X and Y. And then I'm also doing a final write of Y. So nobody else is reading from my write. I'm sorry, nobody else is reading from my write of Y. Okay. So now that, as long as that stays invariant, all my reads, what I'm reading from either initial or another transaction, and the final write I'm doing, as long as that stays invariant, as long as that doesn't change theoretically, then you can move me. So if I'm right here, look at this yellow guy here. He's the read of Z. Is that an initial read of Z? Quickly, well, not quickly. Sorry about that. It's kind of an annoying voice I just made there. Well, if you're going to be quick about it, you'd say, well, no, because he's actually reading. 2 is, yeah, good. So 2 is reading Z from 3. So 3 is writing Z, and 2 is reading it. Okay. Now, the initial read, basically, initial read. Say, well, who did the initial read of Z? Well, actually, in this case here, it was 3. Sometimes you won't have an initial read. I mean, they'll just write it blindly. So there's this issue of what's called a blind write. But Z was, the initial read of Z is right here. Okay, but because of that, if I, now look right here, transaction 1, this other transaction here, that was doing a write of X and a write of Y, they're not saying anything about Z at all. So if I move this read, I hope you can see the point, read of Z here, if I move that to here, where this write is, then that should basically preserve all the initial reads and all the final writes and the reads from, they should all be invariant under that move, okay? And so that basically, and they are. So that would be a way you could jostle the schedule to kind of move it around. Now, it's a combinatorial problem, but if you can jostle it like that and keep those things invariant, and in doing that, produce a serial schedule. So in other words, if you can kind of start jostling these things, and you get them to a point where, oh, it's actually equivalent, because each of those are equivalent. Those are view equivalent. That jostling I was just talking about with initial reads and who you're reading the write from, and the final writes. If all those stay invariant and you jostle the schedule around, and you can reach a serial schedule, then that schedule is said to be view serializable. Okay, so I hope that makes some sense to people. So that is theoretically kind of the ultimate of, yeah, that determines whether or not if the schedule is serializable. So the characters view serializable, it's a sound and complete determination of what is serializable. So this is the truth. Okay, so that's good. But the thing is that there's no real algorithm to do it, because you kind of, I mean, you could in principle do it, but it's like there's well, this NP problems, but it's most likely going to wind up taking an exponential number of it's very, very compute intensive. All right, and the point is that we have a much better way of doing it, which is what we're going to have to do now, which is called conflict serializable. So conflict serializable has to do with looking at what's called the direct serialization graph. All right, so here's how the direct serialization graph works. This graph gets built up. So there's definitions of it, but this is let's stick with intuition here, and you can recover these things here, these definitions, if you want. But I'm not going to go through those painstakingly, because it'll just be a waste of time, really. Because you can go back and study that, and you'll see that it all makes sense. But basically, the way you set up a DSG is that each transaction becomes a node in the graph. All right? Each transaction becomes a node in the graph. Now, if you have a transaction 3 is doing a write of Z here that transaction 2 is reading from. So that's in this invariant about reading from. So transaction 2 is doing its read of Z from transaction 3. Okay, and if you look right up here to say, okay, so transaction 3 is doing its write here of Z, and then transaction 2 is reading that. So that's why you get this write read arc in the direct serialization graph. Okay, now there's also what's called a write arc. So the write arc basically means that the immediate write of something, in this case of Z here, the immediate write that follows the write of Z from 3 is for a T2. So we have these write edges as well. And then we also, by the way, have read write edges. So I did a read, and then the next write was done by some other transaction. So basically the way it works is that as you're going through, as a schedule comes in, you have a node for each of these. And basically as you read the schedule, you determine which arcs you're going to add into the direct serialization graph. Okay? Now, so you add the arcs in, and the arcs of these 3 types: a write write, or a write read. Yeah. So read is the only other combination, and that's not, you don't need to track that. Okay. So you do that. Now, as you're going and you're building that graph, right? You're building this graph of these things as they're doing their operations, and you determine a cycle in the graph, then someone's got to get aborted. Okay. Someone's got to be aborted at that point. And what that will do then is, if you follow that policy, and then, okay, they get aborted. I mean, aborted is not so bad, because in this case, you just get restarted. All right. Maybe I should say it now. Well, I'll talk about transactions being aborted. There's 2 types. Here, I just want to start out and say this right now, because otherwise it's going to be, I'll forget to say it, but I just want to say it now. It's kind of an aside from all this. Transactions are basically of two types. Either they are fully specified little pieces of code that just run, like a deduction, like transferring money from one balance to another, one account to another, or there are things that have a human in the loop, like I read the seats available, I sit there and I scratch my head, I ask my partner, well, what do you think? And okay, and this like that. Okay, I'll take that seat there. Okay, so that is not really something where if it gets aborted, it's kind of like, oh, I have to do that again. So it's annoying. The other one is actually, if it gets aborted, you hardly even notice it because it just kind of gets restarted, right? But you can't restart this process of me selecting a seat. It requires kind of a something from the external world. So it's not really a repeatable, or it's something that's it's hard. You can't really capture the full essence of what the transaction is because there's a human making decision inside the loop of the transaction. All right. So, but okay, that was just an aside. I wanted to just kind of make that kind of aside, which I probably should have waited to say that sometime later because it's not really pertaining to this. I'm sorry. This case here, though, just the fact is that if a loop happens in this DSG, then they're going to pick a transaction that will be aborted, and most likely what they'll do is they'll pick the one that is the youngest. That's kind of a good policy because then you don't get this kind of this kind of live lock problem. So if you're always the older transaction, they've been waiting longer, so let them go through. The younger transaction, well, they can restart. They've got it's do that. Okay, so that might be kind of a heuristic you'll use. All right. So conflict serializable is just is there a loop in that graph? Now the nice thing, what do we have here? Okay, so here's the theorem. Every conflict serializable schedule, so a schedule that gets produced when you're running that graph thing and checking, all of those are also view serializable. All right, they're all view serializable. Now, there are some cases which are really oddball cases, like a case like this. Let's see if I can do this one here. Right one. If I do this. If you try, let's say we try to run this schedule through we try to run this schedule here through the transaction processor, and the conflict serializable processor. It's going to basically build a graph. It's going to have two nodes first, and then it's going to say, oh, now we have a write from 2 to 1, and then we have a write from 1 to 2. Someone has to die. We're going to abort it. So this is not conflict serializable. This will be aborted. Okay. However, this is view serializable because all the final writes. So basically, the final writes, you can permute all these things, and the final write of X is going to always be 2 doing that, and the final write of Y is always going to be 1 doing that. Okay, and you can just kind of move them around, and then you can make it a serial. So this is actually view serializable. So basically, the only time you get like some non-correspondence between view serializable and conflict serializable is when you have what are called blind writes, writing without reading, just writing it out, okay, without reading it. So how often that comes up in practice is, that's really hard to kind of say anything definitive about that. But this is the only thing you have conflict serializable. That's how you're going to implement this. Okay, so that's just that. All right. So I look for questions, and then we'll see 10 minutes. Okay. So realizing this. Okay. All right, so how do we get this implemented? Now, I'm going to go through this really, really quickly because this is not how it gets done anymore in the quote real world. Everybody's using a different way of doing it, but I just want to okay. Basically, here's how it gets done in the real world now. It gets done via multi-versioning, but locking kind of historically is how one goes about this, and it's kind of it's kind of a question whether we should. You can still do locking in PostgreSQL if you want, but it's kind of old-fashioned, and you probably want to just do the multi-version concurrency control. But let's just talk. Let me just kind of go through this really quickly, and I'll have the slides, so it's useful to kind of at least have a little bit of idea. So you have write locks and read locks. The way it works then basically is if you want to do a write, you got to get a write lock. If you want to do a read, you got to get read lock. If you get a write lock, you're also getting a read lock. Okay, so they're kind of, and there's unlock operations. So transactions with locks basically have to kind of follow this locking protocol. So you can't run the transaction through if you're not doing the locking because the system won't let you do it. Okay, basically the way it works. So the schedules become a little bit more kind of cluttered with this locking stuff, and then schedules with locks, they kind of look the same. I think maybe the only thing I just want you guys to hear, because it's like something that it's kind of it comes up sometimes. You'll hear people talk about 2PL, two-phase locking. This is not to be confused with two-phase commit. And two-phase commit is something we actually want to talk about because it's more interesting. And that has to do with kind of doing ACID in, or doing transactions in distributed databases. So that's two-phase commit is actually much more relevant. But basically what happens with two-phase locking is it just basically has to do with like, what you do is if you impose two-phase locking, it just basically means that when transactions get their locks, they can't release them. They can't release the locks until they, well, when they are going to gather locks and then they're going to release locks. And how they do that can be either abrupt, you have to get them all at once, which is very hard because how do you know all the locks you need at the beginning? Or you release them all at once at the end. That maybe makes more sense. But the issue about this is basically that you have a growing phase where you're kind of gathering locks, and then you have a shrinking phase where you're going to release the locks. And you don't do the seesawing where you get some locks, then you get rid of locks, then you get some locks, then you get rid of locks. That will lead to a lot of problems. And what we'll find out is that we can basically get conflict serializable via the locking strategy. But I'm thinking, okay, 2PL with locks. So if you do 2PL with locks, you will get something that's conflict serializable. All right. So it's kind of a way that with the locks that you can actually kind of, you don't have to have the explicit graph, you can do it with the locks. I think, however, that I'm not going to have, I'm not going to include, I think I'm going to actually get rid of locks because it'll make more space for us to do stuff. So I'm maybe just going to remove these slides as well, because I want you to kind of, you can have a slide. Basically, we're not going to do locking because I think that we want to get on to kind of more modern stuff. The one thing we want to talk about then is we want to talk, okay, so the assessment of 2PL, okay. Okay, termination of transactions. Okay, so the deal is this, is that when we, what if a transaction aborts after executing at least one write? Okay, here's the problem. And this actually does, well, I'm just going to skip that. I want to talk about something. Maybe this will come up in a different context. But there's the idea of, this comes up in something called read uncommitted. All right. So there's the idea of a transaction. Let's say I'm a transaction. All right. And I go and I do, I release my locks. Basically what I do is I write something and I haven't committed yet. I write something else and somebody else reads it. Okay. So here's kind of, I just want you guys to know this kind of, this basically this notion of a dirty, it's called a dirty read. Okay. So you're gonna have to, don't look at the slides, just listen to me. Something's called a dirty read. All right. It's when you read dirty data. All right. So you're a transaction. You start, you read some data, you write some data, okay? Then you're gonna go off and you're gonna do some more work. Now I go and I read some data. I'm sorry, I read the data that you wrote, okay? So basically what this is I'm doing a uncommitted read. So I'm reading some of your data that you wrote, and then I say, oh good, I read the data, based on what the value of the data is, I write something and I commit, and the database system says yes, and I think I'm durable, right? Now, somebody then reads from me, and they based all their stuff on what I wrote, and then so we have other people who kind of down the line doing that. Now, let's say that you still haven't committed yet, but then let's say you abort. All right, that means that the stuff that I read from you was dirty. I did a dirty read of what you wrote earlier. So in principle, we should do what's called a cascading rollback. So in other words, so the thing should say, oh no, and they should dig up me, who have already committed, right? I've already committed, and say, no, you can't do that because it was bad data. You did a dirty read. All right. So I hope people understand that that would be problematic. And then everybody else who was depending on me would also need to be rolled back. So we have this cascading rollback of already committed transactions. All right. This is absolutely not going to be acceptable. Absolutely not acceptable. All right. This is going exactly against the D in ACID durability, because I thought I was done, but no, as it turns out, because of some other stuff, you know. All right. So this is, in some ways, I mean, this is like, transactions are very deep, actually, I have to say, because this is kind of like when you look at like some workplace conflict or something, people angry and something had happened with the work and all this, and everybody's going, rah. Actually, what it is a lot of times, you can map it out, and it's basically it's something like this. It's like a dirty read or something like that, where somebody was depending on somebody else that actually shouldn't have, and everybody was innocent enough, but you're getting these concurrency problems or these transaction problems among people. So a lot of times, I mean, a lot of problems in the world are actually transaction problems ultimately, if you want to get kind of deep about it. But all right, so I'm going to play with the slides a little bit to kind of get rid of locks. And I'm going to change this because this is still important, but I'm not going to use the word lock. I want to talk about this right here. Talks about the object that's the subject of the transaction. Now, before I told you guys that it was tuple based. The locks basically are working on a tuple on a tuple basis. Okay, so a lot of times though, the way that works is it doesn't really quite. It doesn't. When you grab locks for a tuple, you also have to grab locks for everything above it. Okay, you have to grab a lock because you're actually going to be affecting. If you're going to be writing to Alice's tuple, then you're also going to be writing to the employee table. So that needs to be. You need to have some kind of lock on that. Okay, or at least some read. Well, there's going to be some type of lock. So this I'm probably just going to get rid of all this because again for time. So speaking of that, I just want to not waste any more of it then. So what we have here in SQL is the standard. So SQL is defined kind of these standard 4 degrees of isolation. So we have read uncommitted, and these are the anomalies that they allow through. So read uncommitted allows for this dirty read, and it allows for the non-repeatable read. So it allows for the idea that what I can do is if I do a read later on in my transaction, I might get something else that somebody else had written. All right, that still remains true under read committed. So this dirty read gets kind of knocked out. So you don't allow for dirty reads, which is very good, and it kind of this is helping with durability quite a bit. All right, then we get the issue of what's called repeatable read. So this means that all your reads are going to be the same. But what this did in classic transaction processing, this allowed for what's called phantoms, which are kind of a strange artifact that I don't really want to get into. It has to do with the locking. It has to do with what you lock, and then if I lock a range of something, right? I'm going to lock all the tuples in that range. I put a lock on every single tuple, but then if something else enters into that range and I query that range again, that new tuple will pop up as what's called a phantom. But the fact is that that's an artifact of locking strategies, and all that's gone for the most part. We're going to multi-versioning because that's much more the way it is, right? The way modern stuff is done. Boy, we're looking for time here. Okay, so let's just finish this up though here. So this is kind of more historical, this business of these kind of isolation levels. Yeah, let's go back. Let's go over these a little bit more. Let's just stick with read uncommitted, read committed, and then serialize. Well, yeah, we'll get into what really happened here. Maybe what I'll do here, I'll just go over some of these levels of these isolation levels, the ones that are going to be important, like the ones that I want us to really look at here are going to be read uncommitted, read committed, and then serializable. Those are the ones we're gonna look at right now. This is for classic SQL, but I promise you we're gonna hop right on over into like what PostgreSQL is and what modern stuff is. We're gonna banish locks. We're not gonna deal with locks. So let's just take our break now at this point and come back at 15 after, and then we'll resume. I'll do some surgery on the slides so I can get rid of locks, because I think that's something that can go, and this will give us more time. That'll free up a lot more time for us to talk about more modern stuff. Okay, good. Let's come back at 15 after, and I'll pause recording. Okay, guys. I think we're back now. Yeah. Maybe it's 14 right now, but all right. So let's continue on here. So I've decided actually I'm going to keep the slides as they are, but I'm not going to cover in recitation. I'm not going to cover anything about two-phase locking. In fact, I'm going to try to avoid most mention of locking in general. But the reason I want to keep them in there is because you guys should maybe know it, because this is kind of one of those kind of classic interview questions. Like if you're going into a job somewhere and they say, well, hey, what's 2PL? What's two-phase locking? You know, it's not that anybody uses it anymore, but they kind of like to see whether you were educated or not. You'll find that a lot of places will do this kind of thing. They'll kind of, I know that, if my company ever gets to a point where I hire people, I'm going to ask them questions like that. I'm not 2PL, obviously, but I'm going to ask them other questions because, you just put people on the spot. I mean, you're hiring the person, you're not hiring them to be a people person. You're hiring them to be technical and to be able to do stuff. And so they got to, it's kind of like, it's a quick litmus test. Sometimes it depends. I mean, but a lot of times, I mean, you'll get, I think that question is being asked to people out there too. What is 2PL? And so you kind of have to know kind of how this kind of classic locking strategy, you might want to look at it and kind of have at least be able to kind of, I mean, the first thing you should tell them if they ask that is that, well, that's not being used anymore. It's multi-version concurrency control. So, but if you want to hear it, then kind of give them a little bit of a definition. This is the classic kind of a way the SQL, here we go to isolation levels. This is the classic way it's defined in the SQL standard. We have read uncommitted that allows for dirty reads. We have read committed, which doesn't allow for dirty reads, but it does have non-repeatable reads. And then we have what's called repeatable read, which is a strange one that allows for these phantoms. We'll see that number 3 here kind of drops out when we go to the modern stuff, which is kind of nice because phantoms are kind of complicated. And then we have serializable, which is kind of should be like the true great transaction level. That is what, if you really want to make things work perfectly, you should run it at serializable. But the SQL standard just simply defines that as the absence of these anomalies. All right. And we'll see how that got things into trouble a little bit, like maybe like 10 years ago. So we'll talk a little bit about that. These are kind of just the definitions of what these are. So the one thing to say about read uncommitted is at least it does correct for the lost update problem. So you can have lost update, that anomaly, nobody accepts that anomaly. If you want to allow for lost update, so you want to just allow for like willy-nilly access and let things clobber each other, because maybe in your application that's good enough, then simply don't use transactions. Don't use transactions and don't begin stuff and end stuff. Now, a lot of your programming language support is kind of implicitly using transactions, like at the connection level. A lot of the Python libraries, they tend to do it that way. So you have to kind of you have to explicitly open fresh connections to kind of block that. But so you might have to trick around with your programming language to get so you really absolutely have no transactions. But if you wanted to allow for, if you wanted to basically just allow for anything, you would do that. But read uncommitted. See, read uncommitted also falls out. That's no longer really supported. What is supported is read committed. So what read committed does, it basically means that you can still have repeatable. Your reads aren't necessarily repeatable. So you might be reading from somebody who just committed, and then somebody else commits, and then you read it, and then you and your transaction lifetime see different versions of the database. So that's your loosest isolation level where you're still running transactions inside, like say PostgreSQL. We'll get to this, shortly. Then there's the repeatable read. Let's just skip that because that just completely dropped out. And then we have serializable, which is kind of, this whole idea that what falls out of this should be view serializable. Now, the truth is that it wasn't because of the way things are being implemented in current databases. So actually, this was an example of academia contributing because a researcher in Australia, a professor in Australia, he discovered that, well, actually, we can have certain strange anomalies that aren't in the SQL definition. They can creep in under the modern version of doing serializable. All right, and this actually set off a lot of work because that meant that there was some kind of flaw in the way it was all being implemented and the way it was being modeled, and that we're going to go into that flaw. And you might say, well, that flaw, that flaw is so infrequent. Why would you really worry that much? Well, we all know why you would worry that much. is that if there is a flaw, if there's a vulnerability, that somebody who wants to get ill-gotten gains is going to exploit that vulnerability. So, the presence of a vulnerability just simply what that is, that's a target. You become a target for people who want to exploit that vulnerability. So you cannot be ignored. So it was kind of a bit of a, it set off a frantic patch of the modern way of doing these things. So it's kind of an interesting story in and of itself. So let's go now to the more modern. Wait a sec. Okay. Let's see here. All right. Where are you? All right. All right. So that was it. 1 second. Can you guys still see my screen share? I'm assuming you can, but it's not really highlighting it anymore. Okay, now we're going to get into something where like it's not just me kind of saying, well, it's not locking, because now we can talk about something that's actually real time, what's going on in the present day. Okay, so single value currency control versus multi-value currency control. All right, so hardly anybody does single value concurrency control anymore. So the basic theory was built on this kind of lock. You have one version of the database and you're doing kind of locking around that one version of the database. What new, more current generation database systems do is what's called multi-version concurrency control. So it's much more expensive memory-wise. Okay, both primary and secondary memories, because what you're going to see, what we're going to do with this is we're going to create a ton of copies of the database. But we can do that now. So let's just step back here and let's just consider that example we were talking about in the beginning, just to kind of form some intuition. So the example we're talking about from the beginning was this example where all of you guys wanted access to the database. So all of you were sitting in a crowd, in the room, and you all wanted access to this database. And my one thing was I said, okay, I'm going to just put a giant lock on the whole database, and I'm just going to basically say, one person can unlock it, they can do their work and then lock it up again, or unlock it rather. And I'm just going to put people in an order and line them up. Okay, so here's another version of what I could do. I could say, oh, you guys all want to do operations on the database. Okay, fine. Here, everybody gets a copy of the database. Right? Here, have a copy. I'm back at Central though, so I hold like the copy of the database, like the licensed, legitimate copy of the database. Now, as some of you do your work, what you do is you just send me in your copy of the database, right? So you took the database, and of course you were isolated because you just worked on it, right? And then you said, I'm done, okay. And then you sent it back to me. I took it in, I said, okay, what did you do? Great. And then I basically merge your changes in with my version of the database, okay? The next person, they send theirs. People. Now, somebody sends it at one point, I say, I can't merge this in. No, the changes you've made, sorry, I can't. You're overwriting somebody else's. There will be a lost update if I accept your changes as they are. So instead, what I'll say is okay, no, you abort, and I'm going to give you a fresh copy of the database, and now you can work from that and do what you were going to do. All right. So that right there is this kind of idea of doing these snapshots of the database and me just kind of throwing them out, distributing them. So I hope intuitively you kind of see what I mean by this. And it's an alternative way of solving it. Now it might be that like a person, so I get several of you guys clear your transactions, and then a couple more of you are getting aborted, but then you get rerun, and then you clear yours until the final analysis. We drive through the whole. Everybody gets their work done. Right? Somebody might have had to kind of repeat it a couple times and was annoyed, but that's life. So, but still, we have then basically we can recover a serial schedule that was all that work, right? Okay, so that right there is kind of the intuition that surrounds this MVCC, right? Multi-version concurrency control. So we're maintaining multiple versions. So let's get a little bit more kind of specifics about this. So we have transactions. Let's just talk about the version of X, Y, and Z. So we have these data values X, Y, and Z. They can be 3 different tuples or something. And then what we basically say here is we say that we have the global version, which is the truth, basically, or what we consider to be the truth. And that basically the version of X, A, B, and C, these different transactions all have their own copy of X. and transactions C and D have a version of Y, and D and A have a version of Z. So when I say that basically transaction D is going to now read Y and then write Z, so they read in Y, all right? And so they'll have their own little copy of Y. And then what they do is they actually write out their version of Z here. Okay, so look what happens here now. So what happens now is this global pointer now gets pointed at the version that used to be the property of transaction D. All right, but now it's pointing here. So it's just, we're doing these pointers, we're changing the pointers to affect the copying. Okay, and the old version of Z is now just going to become garbage, and it's going to be up for garbage collection, which in database terms is called up for vacuuming. It's going to be vacuumed, right? So there's going to be an explicit process where we're going to go through and we're going to vacuum up all like the garbage inside of our tables, because we're playing all these pointer games with these old copies that being abandoned and not having any reference to them anymore. And if we look right here, what happens is that when when transaction D commits, that the copy it had, the little local copy it had of Y, that becomes garbage, because it doesn't need it anymore. These other ones just stay the same, right, on version X. This wasn't even touched. So this is kind of how it's done, right? So it's done with pointers to like what the latest. Okay, good. Here we have a question, a direct question. So maybe I'll. Okay, yeah. So when I was talking about the example of just making a copy of the database, that was more in principle what was being done. In principle, I was making a copy of the database and sending all of you guys a copy that you're going to work on, and then I'm going to merge back. But in practice, what we're really doing, we're doing something much more optimal, and we're doing exactly what I'm presenting on the slide here. We're playing kind of little pointer swap games. So I'm actually not giving you a full copy of the database. What I'm doing is I'm saying, here, have the database. You have a full copy. And then as you read stuff, what you're going to wind up getting, basically what's going to happen is I'm going to at least kind of snapshot it so that you're going to be reading the version of all the objects that as they were of the exact time you started. But then the thing is that you'll only actually in truth be bringing the memory that you're using. All right. I hope that makes sense. And then as but it is more memory intensive. There's no doubt about that. That it's a lot more memory intensive than single value, where we're doing everything through locks. All right, but now we can do this. So I hope that answered the question, which was a direct message question. So but just let me know if you want to follow up, because I can talk a bit more about that. But I hope that answered it. That in truth, it's not that wasteful. Yeah. Okay. Good. I mean, it's not as wasteful as I. The picture I painted though was nice because it's intuitive, but it's not. The actual implementation uses this kind of pointer. Playing with pointers and doing vacuuming. Okay, so then insertion is basically just like you want to insert a fresh tuple, then basically it's just what you do is you just create it in your own database, and then just make a pointer to it, and then the global can take that pointer later. Okay, so basically a version of X before commit. So before commit, it's like a version of A rather. So I think it's creating A. Transaction A is going to create a new version of X. So transaction A and transaction B are both creating a new version of A. I'm sorry, a new version of X. A is creating a new version of X, and B is creating one. They're both doing it. And then A commits, and that means then what will happen then is that it's going to be the global version of X is now going to point to what A's copy was, because it just created it. Now, B is going to be in trouble when it tries to do its commit, because it's not going to be able to merge that in. All right. So this is an example of two transactions creating something the same, maybe the same kind of thing with the same primary key or something, and then the second transaction is going to have a problem once it tries to commit. Deletion's easy. Deletion is just basically turn something into garbage. Right. You just the pointer to the object turns into garbage, and then it'll once you commit, it's just going to point that to garbage. Okay. So motivation for studying lock-based currency control. And I think the motivation is that the only motivation I have now is that you should kind of at least be able to say what 2PL is, because somebody might ask you that on an interview question. That's the one. Well, I mean, knowing about locking, I mean, there's a kind of a trade-off here, right, between keeping a single version and putting locks over it, or having a protocol around having multiple versions. So that there's kind of an interesting kind of trade-off between multi-versioning, either you do multi-versioning or you do locking, right? So, but as we'll see, actually, the truth is that PostgreSQL is still doing locking, and we're going to see that come up in just 1 second. And we're going to kind of describe why it's going to be using locks. So nothing is so simple ever in transaction processing. But basically, the theory that we presented in the first lecture, it's still, I mean, certainly the theory about view serializability and conflict serializability is very much valid. That is going to be true to the end of time. But the locking protocols in 2PL, that stuff has kind of been antiquated by MVCC. All right. I don't think we need to go over it. Okay, so for multi-valid concurrency control, there are kind of 2 fundamental modes of doing it. All right, there is the snapshot mode, and basically what the snapshot mode means, it means that when you start as a transaction, snapshot is much more intuitive, right? What snapshot basically says, it says when you start at one particular time, you're taking a snapshot of the database at that exact time, and all of your work over that will be over that snapshot. So it's never gonna, nobody else, you're gonna be perfectly isolated in the sense that nobody else is gonna come in and your version of the database won't change underneath the hood or underneath you as you're doing your operations. You might have a problem doing a commit later, but at least you're isolated until you get to the point of like dealing with commits. All right. Another way, and this is actually the default behavior of PostgreSQL, is to do what's called read committed dynamic mode, or read committed. Basically, it's called read committed. In this mode, basically the reads of data objects which the transaction is not yet written are always made from the latest committed version of that object. So in other words, you do have non-repeatable reads. So if you start out and then you read something and then you read it again later, you might get a fresher version of somebody else that committed that. Okay, so this is a kind of version of read committed that is going under multi-version concurrency control. But once you have written the data, so once you actually wrote the data yourself, then it will be solid, stable for the rest of your transaction. Okay, so you won't, even if somebody else did a commit on it, it's going to be stable. This is used inside of PostgreSQL. So when you basically say read committed, or as it turns out, read uncommitted, both read committed, when you set it in SQL to like the isolation level as read committed, this is what you're going to get. You're going to get this read committed dynamic mode, which we'll cover in a second. We'll show kind of what it means, kind of more implementation wise in a second. But if you also say read uncommitted, you'll also get that. It's very, very confusing, but there's no difference in PostgreSQL between read committed and read uncommitted. It's an unfortunate just kind of quirk in the, well, it's just because things changed a lot when you went to MVCC. Just the way things get implemented. It's okay. So read committed. So we talk about read committed. This one. So in this case, if we're under RC, we're under read committed. Basically, what this means is that all the reads are made from the unique current version, committed version of the database. It's not really good. There's not really good intuition about it so much. But as I do the reads, then I go back to the current committed. So that might change. Somebody else might commit as I'm going through my transaction. The issue is basically how do we deal with update conflicts? Okay, so the easiest way to do this. So an update conflict, of course, means that if basically you have 2 transactions overlapping in time, and they both want to write the same object. Okay, so it's like I make a copy of the database where we're all going under read committed, and I do this kind of thing where I share out the database in this strange way to everybody in the class, and then it's like under the pure case where it's like kind of I just wait for people to kind of finish with their database and send me a fresh copy or the copy that they've changed. That is I'm determining whether or not you're going to be able to either succeed or fail at the transaction at the end of the transaction when you're actually committing. You're saying, okay, I'm done, I'm committing, and then it fails. That's not now. That's basically a first committer wins type of strategy. So basically what it says whoever can commit first is going to, and if there are two that are in conflict, two of you both wanted, I send out the database and two of you both wanted to write the same data object, then whoever sends it back to me for the first is the one who's going to go through. The other one's going to have to reread it and redo, okay? That's under first committer, but actually the way PostgreSQL does the first updater. So the first one to actually make an update on the object gets a lock on the object. So there actually is locking going on in PostgreSQL's version of read committed. Okay, so that if you go and you actually grab something, you make an update, you read it and then you write it. Once you write it, you're getting the lock on it, and then what'll happen then is you'll there's some protocol around. Well, if another one who's then wants to get that, what they'll do is they'll be blocked. So they try to get a right lock on that too, or they try to write the object. They get blocked, and they're waiting for the possibility that you abort. If you abort, then they can grab it. But if you commit, then they abort, right? Because there's a conflict. So that's how it actually gets implemented, and you have to actually do that with locks. So it kind of gets complicated. So this first updater wins is actually how PostgreSQL is going to implement this. All right. Now, that just has to do with this read committed level here. You're getting this contention. All right. So now we get to like this thing of snapshot isolation, which is kind of nice, the nicer one, because it's kind of simpler and purer. That is that the private version, you get a snapshot and then you work on the snapshot, and there's no non-repeatable read. So basically, this also is implemented under some locking where the first updater wins. So there are locks going on underneath the hood. I mean, you could make it so that you said, I mean, if we were being purist about it, we said, no, we're doing multi-version concurrency control. We're not going to have any locks at all. The problem is these transactions get so deep into them, and then they try to commit and then they fail. Sometimes it's better just to have it so that you have some kind of locking so early on, so that that a transaction that gets blocked can just fail itself, or there's a bit more flexibility around that. So as just a practical matter, it seems that this first updater wins seems to be what people want, what customers want in terms of their transaction processing. So there's that's the benefit of it. Okay, so let's look at snapshot isolation, and let's just talk about that. All right, so snapshot isolation is the idea behind that was basically that, well, you can't have dirty reads, of course, and you can't have dirty reads under read committed either, and you can't have non-repeatable reads because you only have one version that you're always going to be working with. So thus, this isolation level at the level and you're not going to have phantoms and all that because you only have this snapshot you took of the database when you started. So at the level of SQL and the SQL standard and its description of isolation levels based on the absence of anomalies, based on that, then this should actually be serializable. All right, this should be this idea of doing snapshot isolation should be serializable, and serializable in the SQL standard. But the question is it view serializable? Is it the truth? Is it truly serializable? And the answer is no, it isn't. And there are several anomalies that you can kind of look at. Some of them are more easy to understand than others, but we can have several anomalies that allow for that. One's called write skew, and one's called the read-only anomaly, which is kind of hard to really explain here. And there's a third one, which I think is kind of really gives you an intuition about why snapshot isolation is not producing view serializable schedules. So write skew has to do with the following. So if you have an integrity constraint, so you have this extra integrity constraint that basically says X and Y must remain above 500 euros. And the initial state is that the X and Y are both 300. So that is, it's maintaining the constraint. It's greater than or equal to 500 euros. And then transaction 1 is just going to take 100 euros from X, and transaction 2 is going to take 100 euros from Y. All right. So both of these actually will be allowed to run through. And the reason why is because they check and they say that, well, X plus Y is always going to be above 500 because greater than or equal to 500. Because when I take transaction 1, what it does is it reads that it takes a snapshot of the database, says, okay, X is equal to 300, Y is equal to 300. I'm going to take 100 from X, fine. So then I have 200 and 300, but that's still above 500. The sum is still above 500. So that's A-okay. And I'm going to write out to the database my new version of X, which is changed to 200. And the same thing is going to happen with transaction 2. And then in the end, we're going to get the final state under this snapshot isolation scheme. We're going to get the final state of 200, 200. But that violates the constraint that both need to be above, the sum of both needs to be above 500, 500 or above. Okay, so this is called right skew. So basically, this doesn't involve any dirty reads. It doesn't repeat and non-repeat reads. So really, it passes the SQL definition of serializable. But obviously, you cannot form this is not view serializable, because you cannot have a serial schedule that would go through. Because if 1 went first, then 2 could not go through. And if 2 went first, then 1 could not go through. All right. So what basically would say is that 2 would basically, the result of 2, if it 1 and then 2, then 2 would basically, the result of that transaction would basically be, well, abort, or it would be signal, like send an error message saying that we can't do this. It would not allow it to happen. So that's a problem. Okay, so this is the weakness that was identified. So they weren't really aware of this when they just declared, because they were just kind of going by the SQL standard. So PostgreSQL version 9.1, or all of them before version 9.1, actually was misleading people into saying that if you want a serializable schedule, you want a serial schedule, well, it would still allow for this kind of thing to happen. So there was an anomaly was being let through in an older implementation of PostgreSQL, and not just PostgreSQL, but all of the MVCCs that were out there on the market. They were all letting this anomaly through. So that's bad. All right. So then they had to kind of like deal with that. Now, another one that I think it makes a lot of sense here, that there's a little bit of formalism around it, but just think of it the following way. You have this kind of cycle here where I read a value. Let's say that we just have like, I basically say, I'm going to read tuple number 7, and then I'm going to write to tuple number 8. Another transaction is going to read tuple number 8 and then write to tuple number 9. And we're going to go until we get to, let's say, tuple number 10. And the transaction that's doing tuple number 10 is going to read tuple number 10 and write tuple 0. So it's a big chain, right? It's a big loop, right? So what we're doing is we're basically doing a shift. I'm basically taking a value from tuple 1, moving it to tuple 2. That's transaction 1. Transaction 6 is I'm taking a value from tuple 6 and I'm writing into tuple 7. So I hope you guys see that there's a big cycle being formed of things all being kind of moved along, okay? Now, intuition will just tell you this, is that no matter what serial schedule you pick, somebody's data is going to get clobbered, right? Give me an order that you could run the thing so that data wasn't lost. There wasn't like a missing, something didn't get clobbered. Oh, you say, I'll do 1 at first. So what 1 does, it copies it to 2. Okay. Now, what will happen is that number 9 will copy it to 10. And then finally, at the end, well, if the last one that runs is like the 10th transaction goes from 10 to 0, it's going to copy that fresh copy that was, I guess, 9 before. So something's going to get clobbered. If you think about it, just kind of, there's no way to do this in a serial way where, you need to have like a little temporary variable somewhere that things get copied into, right? And something like this. So that is an example of, now that would work perfectly under serializable, but it's not view serializable. So it'll work perfectly under snapshot isolation, what used to be called serial, but that's not a view serializable schedule no matter what. But it would do it under snapshot isolation. Okay, so that's another example, kind of intuitive example of where the anomaly comes up. All right, so this set off a lot of problems, right? So people were like, uh-oh, what do we do? And so they basically, it didn't take long to kind of figure it out that what you need to do is you need to kind of you need to add some extra mechanism to snapshot isolation to basically implement what's called serializable snapshot isolation. All right. So serializable snapshot isolation is basically resurrecting this direct serialization graph, and it's looking at the direct serialization graph and waiting to see if certain types of what are called dangerous structures are arising, okay? And if these dangerous structures arise, then it's going to have to pick somebody to abort. So it's just this extra level on top of snapshot isolation, a little extra level of implementation that has a direct serialization graph where it's looking to see certain patterns arising in that direct serialization graph which then says, okay, we gotta abort one of these transactions. All right, so the direct serialization graph, if you recall, is this thing where we have the transactions, we have write reads, read writes, and write links between them. So we covered that in the first hour. And so if we look at something like this, then basically what we're looking at here now is we're looking for these, all right, so okay, here's a fact. Okay, so if we look back here at this direct serialization graph for this particular schedule here, then basically of the three types of conflicts, read write, write write, and write read, the only type which may occur between concurrent transactions, so transactions that are running at the same time, is a read write conflict. Okay, so in other words, they both read the same value, and then now they're both trying to write the same value, right? Or well, one reads first, and then the other one's going to write that. Okay, that's the other one. The and then a write write. Actually, that's the one where they're both going to be doing writing at the same time. But the read write never occurs. The read write never actually occurs because of the nature of the snapshot, right? So I don't. So if we say there's write read, so the first one writes and the other one reads. So these are the concurrent transactions. So let's say that transaction I is starting, then transaction J is starting just a little bit after, but they're concurrent because they're overlapping in time. Okay, so there's a possibility that transaction the transaction I here has wrote something, and then when transaction J starts, it's going to be reading what transaction I wrote. Okay, and then there's also the possibility that they're both going to try to write the same object. Okay, let's see. I'm sorry, I had that wrong. It's the read write is the only one. The only type of conflict between these, the only type which can actually occur is the read write conflict. Okay, so there's only one type of conflict that can occur. These other ones basically determine that that they're not concurrent. So like so what I was saying before, let's just kind of go through this so we have it so it's clear enough. So if transaction so we have transaction I starts before transaction J, okay, but they're going to overlap in time. Now, if I say, so basically what that means, if it's snapshot isolation, what it's going to basically say is it's going to say that I do my writes at the end of at the end when I'm committing. Okay, so if it happens to be I do a write, so I'm only going to do my write at the very end. I is only do its write at the very end of its processing, right, at the end of its transaction. So if it's write read, that means that, well, J read from a write of I, which means that they're not concurrent. They can't be occurring in overlapping time spans, right? Does that make sense? I hope. All right. Then let's look at the other one here. And then what about write write? A write write conflict. I write and then the other one writes. Well, since it only happens at the very end, the writing only happens at the very end, then basically, if I write, basically what would happen here is that it would be, we both read, let's see, we both do a write. We're both trying to do a write. So that's going to be a conflict. We're going to be having a conflict. So I'm going to try to write something, you're going to try to write something, then we're basically not going to be able to let that go through. It's going to basically be in conflict and be thrown away. But we can have a conflict of the type read write. So in other words, I read something and then you're trying to write it, and then we're overlapping in time. We can have this conflict. Okay, so the write immediately, since the concurrent transactions running SI may not write the same beta object, right? So this will get flagged by just whatever kind of resolve them. Write read, since since the read of J occurs when it starts, and the write occurs when it commits. So there's no overlap possible. So I hope you guys can see that you can kind of reason through this. I didn't do a really good job of explaining it because I kind of got it wrong when I started out. But basically what this does is it really simplifies just the kind of the DSGs that are going to be plopping out, that are going to be just, okay, we're going to be running the snapshot isolation, and therefore we could be building these DSGs as we're going along. And what this is basically saying is it's saying the types of DSGs that are going to plop out of this thing are going to only be DSGs which are going to have the read-write conflict, and that's the only one it can have. Otherwise, it could never have plopped out of something running under snapshot isolation. Okay, so it's kind of a simplification, or it's basically it's a simplification of the problem, because it's basically saying these are the only kind of legitimate DSGs we could actually wind up having. The ones that they only are going to have the read-write conflict. Okay, so characterization of non-serializability under snapshot isolation. So a vulnerable edge in basically the way it works is that two transactions, J, are concurrent if they overlap in time, of course. Observation, okay, the transaction cannot be concurrent. Yeah, we already established that. A vulnerable edge. In a read-write conflict between concurrent transactions, read-write is dangerous, is a vulnerable edge, okay? So that's just an edge that we have to kind of keep our eye on. Now, if there happens to be two of these, two consecutive vulnerable edges, which may or may not form a cycle. So we basically have a read-write and then a read-write, and two of those lined up. If we wind up getting that in the DSG, that's what's called a dangerous structure. And the first implementation of snapshot serializable says basically, if these dangerous structures arise, then we're going to abort one of the transactions to break up the dangerous structure. So this, of course, the research has gone on much beyond this. So there's much more finesse in terms of implementation, but this is kind of the emergency way to kind of guarantee true view serializability under snapshot isolation. So there's a theorem here that basically says, if you have a set of transactions, all transactions running under snapshot isolation, if every cycle in the DSG is free of dangerous structures. So if you look at all the cycles in the DSG, and all those cycles are free of these dangerous structures, then we can say that it's conflict serializable. And if it's conflict serializable, then it's also view serializable. So what that means then is, it means that searching for dangerous structures is the initial algorithm to kind of apply to do this. So detection, here's an example here. So if we look right here, this is the example we had before of the write skew. We had the read write on Y because, and we have the read write on X, because X is basically what's happening here is transaction 1 is trying to write X, and transaction 2 is trying to write Y. And the transaction 2 has read X, and transaction 1 has read Y. Okay, and that's why we get this here. So we look at this cycle here, and we see that there's this is a dangerous structure. This forms a dangerous structure. So it doesn't matter what is here. If it basically forms a dangerous structure, then it's going to be we're going to have to abort one of them. Okay, so this just shows you right here that using this kind of algorithm, or this kind of way of looking at it, we can actually remove. We can see that one of them has to be aborted. So if we run under this, then we wind up getting this is for that non-serializable read-write thing. Okay, so the implementation of snapshot isolation. Well. Okay, this I'm not going to get into. This is kind of a bit too much. So we're going to get, basically the implementation side of PostgreSQL is it's much more complicated than just looking for single dangerous structures. They've got this potentially dangerous structures, and there's a whole set of algorithms that people have been developing. And I'm not really sure where it stands at this point, but they set off a lot of activity to get more and more efficient ones. But at least what we can do is we can basically say under serializable snapshot isolation, we get view serializable. We get or we get conflict serializable, which means it's also going to be view serializable. So this is the truth. So we get this. We remove all the anomalies once we go up to serializable snapshot isolation. All right. So yeah, PostgreSQL version 9.1 was the first one that implemented this after the after the recognition of this, or the discovery of this problem in academia. So academia had a good impact there. especially the more extended algorithms, performance is reasonable. Okay, but there's a cost. It doesn't, it doesn't come for free. All right. So now, if we look at PostgreSQL and concurrency control in PostgreSQL, so this is good. We're making really good time here. Okay. So we have the basic idea that you say begin a transaction, and when you begin the transaction, you can set the isolation level. Now, and then when you're using some kind of programming language interface in, then you can do that in the libraries. You can set the transaction level. And so what you have is now you have basically serializable, repeatable read committed, and read uncommitted. These are all available because these are part of the SQL syntax. Now, what happens actually in PostgreSQL is if you say read uncommitted and read committed, those basically become this dynamic read committed that which is the default, by the way, in PostgreSQL. And if you say repeatable read, then you get just kind of classic snapshot isolation, which allows for the anomalies to go through. And if you pick serial, then you're going to get serializable snapshot isolation. So there's really only 3 levels that you can pick in PostgreSQL. If you say repeatable read or non-repeatable read, you get read. Sorry, if you put in read committed or read uncommitted, then you wind up getting read committed dynamic. And if you put in the repeatable read, you wind up getting snapshot isolation. And if you put in the serial, you get serializable snapshot isolation. So that's kind of how it changed in terms of how, so there's not really a clean correspondence now in the SQL naming convention and actually what gets implemented under the hood. But this is kind of, I think all the other database systems like SQLite, SQLite is a different story. MySQL and Oracle and all that, they basically do the same thing. This is kind of what the things have arrived at. Concurrent isolation, yeah. Yeah, so then you have the notion of basically how like the host language deals with, like session-based means for every connection, every cursor basically that you open up to the, well, you have a connection, then you open a cursor. Basically every fresh connection is a session basically, and they's all kind of implicitly defining a transaction. This can kind of get a little bit complicated because it's very much like the Python libraries they've standardized this at least. So there's kind of a standard way this gets done but these are all kind of, you have to kind of dig into the library that you're using to connect to the database to kind of really figure out how the transactions are being done. But they're always being done at one level or another. And you can do like explicit rollbacks and commits. Let's see. Oh, that was it. All right. That's great. We got through a lot here. And so this means we can really kind of look at some more modern stuff. Like, I mean, here, let's see. 1-2 minutes. Okay. Yeah. So basically that right there, I think this is good. I think that this is good that we went through this as quick as we did, because now what we want to do is we want to look at some kind of really kind of more, let's say, interesting stuff where we're talking about like, stuff like, okay, like you guys all heard like, the blockchain and stuff like that. So more like the distributed stuff. So what we're going to do is when we come back, I'm going to review some of this based on kind of like, I'm going to develop the recitation. And then what we're going to do is we're going to kind of like talk a little bit about the next lecture, which is, I guess, on next Tuesday. We're going to talk about the recitation a little bit. And then I'm going to try to maybe explore some of the, explore this kind of at a more practical level, so we can kind of look and really see how we can use this stuff. Transactions are a tricky thing in the sense that nobody says like, oh, I need help with my transaction processing and it's kind of, it's so intimate. Like when you design a system and you build something out, I mean, transactions are kind of really at the root of it all. So if transactions become much more important, if you're actually a full stack developer or you're like working with a big team and you're going to kind of design this big solution, it's not the kind of thing you would be called in to help with. It's more the kind of thing that you would be around at the design phase, and you'd be kind of like scratching your head saying, well, we've got to make sure that number one, we get pretty good throughput on the system. And number two, we've got to make sure that we don't allow for weird stuff to happen that might be exploited. There's kind of an interesting story about how, when I tell you that that PostgreSQL and all the other ones default to read committed, there is actually an interesting story about this Bitcoin bank or whatever, that they basically got ripped off because they sent it. Everything was under read committed, and one entity was able to open 2 accounts and then issue a whole ton of simultaneous transactions where they were basically moving money from the one account to the other, and it wasn't, because it was under read committed, it wasn't able to detect that, and they were able to bankrupt the Bitcoin exchange. So generally speaking, I mean, what they should have done if they had it to do over again, they should have put it under like snapshot. At least they should put it under snapshot isolation. But they didn't. So I mean, there are cases where if you don't set the transactions right, I mean, you can be toast in terms of the real world. Because maybe I can dig into that story a little bit to keep it a bit more specificity and find out what really happened. But okay, so good. So we're basically done with transactions in terms of like the initial kind of sweep over them. And then next lecture, we're going to kind of go in kind of like maybe try to get more of a useful kind of orientation around these. Are there any questions? So the slides are up, and yeah, it's worth studying. I mean, if you didn't get all that, don't worry. I mean, transactions are tricky, but they're kind of interesting, I think. So, all right. So if there are any questions, then say them. Otherwise, we'll just leave it at that, and I'll see you all on Tuesday. And yeah. Okay. Great. I'll just, in this case, I don't see any questions, so I'll just stop recording.